Welcome to another lesson of sectoral structures theory. This lesson today is touched upon in chapter 6 of the book Sectoral Structures Theory. However, today we will go into much greater depth and make a few corrections as well. The title of today's lesson is the Sine Functor of sectoral structures, as well as constant sign structures. In the book, I refer to them as sign regular structures, and hence you will see the abbreviation SR for sign regular, which is fine. But just to make it clearer what we're talking about in this video, I will refer to them also as constant sign sectoral structures. We will do a lot of algebra and a lot of number theory today, but it is very satisfying lesson and definitely very mathematically interesting. So, we will talk about what a sign regular or a constant sign structure is. Let's say we have a sectoral structure, AN, that can be expressed in the form Wi from I equals 1 to lambda. So Wi is the weight of each part, and then 1 to lambda is the number of parts or the order of the sectoral structure, which is lambda. We will define the sine functor. In this case, we're just going to say S bar as a function that takes a sectoral structure and outputs a group of sign values. So from Stn to R to the x. If An has an order of lambda, then this will be R to the lambda. So there is a homogeneity between the number of sign values and the order of the sectoral structure. And we will define S bar of An as the group of, or as the set or the ordered set of numbers from I equals 1 to lambda of sine Ci. So let's take it one at a time. So Ci is the arc length of part I. So for example, if we have this sectoral structure, let's say this has a weight of 3. Its Ci in this case will be the length of this arc, as we saw in the last lesson, which can also be expressed as Wi times phi, with phi being 2 pi divided by n, or the degree of the sectoral structure, and you can refer to the prior lesson for this. But basically, what we're looking at here is sine of Ci. Okay? So for this reason, we refer to this as a sine functor, because again, as we saw in the prior lesson, here we start with a sectoral structure, and if we ended up with just one value, one numerical value, we would call it a functional, a sectoral functional. However, because we're going to end with a group of values that cannot be reduced into a sectoral structure, we call this a sine functor, where S bar of An belongs to R to the power of lambda. So lambda again is the order of An. For example, let's look at the sectoral structure 3, 2, 1 subscript 6. This is a sectoral structure of degree 6 and order 3. We will first need to identify the arc length for each of these, and this will be something like this. The first one, the first part, the 3, which is half of 6, will be an arc length of pi, and this will be divided into 3 sectors. The second part will be 2 over 6, so 1/3 of 2 pi, so that's 2 pi over 3. So this will be something like this, and it will be divided into 2 sectors. And then finally we have the last part, which is pi over 3, and it will look something like this, and it is only one sector. So notice that this, if we stopped only at this would not be a functor, because this is something we can somehow reduce into a sectoral structure. If we divide by pi and we multiply by the common denominator of the fractions, we can simplify this into a sectoral structure. However, because we're taking the sine of these, we will refer to this as, and just a quick point, if we stopped here, we would call this an isofunction, or an isofunction of a sectoral structure, because this pi, 2 pi over 3, pi over 3 is not a sectoral structure. The sectoral structure must be natural numbers only. But because it is isomorphic to a sectoral structure, we would call it an isofunction. However, we're taking sine of these and we end up with 0, square root of 3 over 2, square root of 3 over 2. This cannot be turned into a sectoral structure and is not isomorphic to a sectoral structure. So therefore we call S bar a sectoral functor. And this belongs to R cubed. Now, what do we mean when we talk about sine regular or constant sine sectoral structures? Those would be sectoral structures where every part of this result is equal. So this is almost sine constant, but it's not, because there is a 0 here. Had this been square root of 3 over 2 and all of them were square root of 3 over 2, we would say this is a constant sine sectoral structure. And we will see that those have a lot of specific mathematics and especially number theory associated with them. So now we got that definition out of the way. We will now divide the constant sine structures into 3 main categories. So again, we are using SR for constant sine, which is really sine regular in the book. And there are 3 types of those. Now in the book, we only really address 2 types. And that's why it's important for me to make this video, because the third type is really the most interesting. So if we think about it, we want a sectoral structure such that the sine of all its arc length is equal. So the simplest way to do this would be to have equal arc length. And we've seen again in, I think, 2 lessons ago, that by definition, a sectoral structure whose parts all have equal arc length will also all have the same weight, and therefore we call these unitary sectoral structures. So we used U subscript n for those, but in this case we will call them SR0 subscript n. So SR0 subscript n are basically the unitary structures, the same thing, but just to make it easier for this lesson, more consistent. And we saw earlier that it's very easy to figure out the number of unitary sectoral structures of a given degree. And you can again watch that video for more detail, but basically if the degree of a sectoral structure is n, or let's say if we have a sectoral set of all sectoral structures of degree n, then the subset of unitary structures within that will be equal to the divisor function of n. So here we see our first connection to number theory. Now the divisor function, we've been using the letter d to indicate it, d of n. However, in this particular video, we will use sigma. Don't confuse this, please, with the sigma bar function, which we saw earlier. So this will not have a bar, it will just be sigma subscript 0. So sigma subscript 0 will be the divisor function of n. So sigma 0 subscript 0 of n. So now we figured out how many sine regular structures of degree n exist within a set such that they are unitary. So we could stop here, but then we realized something very important, that there's a lot more sine regular structures than that. Otherwise, we wouldn't have to study them. So let's begin with a very important trigonometric identity. Sine of pi minus theta equals sine of theta. So this is very important. In this case, we will say sine of pi minus ci is equal to sine of ci. So what is this really saying? So this is an arc length of pi. And let's call this here an arc length of ci. Then what is left, if we subtract pi minus ci, will be cj. So what can we tell about cj and ci? They add up to pi. So this is very simple. So then all we have to do is figure out the sectoral structures whose parts add up to pi, or whose each of its two parts add up to pi. So basically, if we have a, let's look at a 1 squared subscript 2 sectoral structure, arc of this type, and let's look at all the structures that are isomorphic to it, then what we need is to divide each of these parts into two parts that add up to pi. So we need this to add up. So with I and j here should add up to pi, and I and j here should add up to pi. But because we want all the signs to be equal in both parts, the I here and the I here must be equal, and the j here and the j here must be equal. So it can't be I plus j and then w plus v. They have to all be the same. So we figured out another important way to find the sine regular structures. So they have to be, first of all, they have to, let's say they are of degree n. They must have a sectoral structure that is isomorphic to 1 squared subscript 2, which are the two arc lengths of pi. In other words, it must have an even degree. So that's the key first point. So the degree of the sectoral structure must be even for this to work. Second point, it must be made up of 4 parts. So lambda must be 4, as we saw, because we're going to divide each of the pies, each of the pi arcs into 2 sections. So it must have a lambda of 4. And finally, it must be made up of, we said 4 parts. Each 2 must be equivalent, such that Cj equals pi minus Ci. So each two parts, if we take two of these four parts, they are either equal or they add up to pi. So that's the rule. And we will refer to these as SR1 subscript n. So a sectoral structure of that form. We saw the unitary, we said SR0 subscript n. These we will call SR1 subscript n. So let's say we have a sectoral set of degree n, so all the sectoral structures of degree n. How many sine regular or constant sine structures do we have of the type SR1? So we can figure this out as follows. We'll start with the rule Cj equals pi minus Ci. We know that we can express this using the weight of the sectoral structure, of the sectoral parts, and we will say Wj times phi equals pi minus Wi times phi. So let's rearrange this. We get Wj phi plus Wi phi equals pi. Let's factor out the phi. We are left then with Wj plus Wi equals pi divided by phi. And what is phi? Phi is the arc length of one sector, which is 2 pi divided by n. We substitute that and we end up with n over 2. So here is our key finding. Wj plus Wi must equal to n over 2. So for example, let's say we are looking at the set of sectoral structures of degree 6. Then for a sine regular structure, it must be made up of 4 parts, such that each two are equal, and such that the unequal parts must add up to n over 3, which is n over 2, which is 6 over 2, which is 3. So the weight of the two unequal parts must add up to 3. And since they're natural numbers, we know it must be 2 and 1. So we figured out what the sine regular structure of type 1 will be for the degree 6. So it would be 2, 1, 2, 1, subscript 6. And if we do the sine for each of these arcs, they will all be equal to each other. However, we can rearrange the parts and still have a sine regular structure. So it doesn't have to be 2, 1, 2, 1. It can be 2, 1, 1, 2. It can be 1, 2, 2, 1. And it can be 2, 2, 1, 1. So we have 4 ways to rearrange the parts. So more generally, we will say that we can arrange them as AB, A squared, B squared, A, B squared, A, B, or B, A squared, B. Now, for the case of 6, we only had one option. Let's look at the the sectoral structures of degree 10. N over 2 in this case is 5. So the parts must be either 4 plus 1 or 3 plus 2. And for each of these, there is 4 options. So we have 8 possibilities. So it's very easy to figure it out. Now let's look at another example, which is the degree 8 structures. So the degree 8 structures, again, half of 8 is 4. So we want the natural numbers that add up to 4. So 3 plus 1, that would work, and we have 4 possibilities. But the other possibility is 2 plus 2. Now notice if we use 2 plus 2, then the result will be 2, 2, 2, 2. And that is a unitary structure. So that belongs to SR0. And in order for us to keep our calculations clean, we will say that if a structure belongs to SR0, then it is automatically disqualified from belonging to SR1. And this will make things easier for us. So we will add one more criteria here, that A is greater than B when we figure out our possibilities. So we saw the example of SR1 subscript 10. So the group of sectoral structures of degree 10 that are SR1 are basically those that have parts Wi and Wj that add up to 5. So that could be 1 and 4 or 2 and 3. And then we have 4 possibilities for each. So 4 times 2 equals 8. So that's the size of the group. Generally speaking, we will now define the size of an SR1 subscript 2k group. So we're going to say n is equal to 2k to indicate that it is an even number. And it will simply be 4 multiplied by the floor function, or rounding down, of k minus 1 divided by 2. And you can try to deduce this on your own as well. So let's say let's say n is 14. That means k is 7. 7 minus 1 is 6. 6 divided by 2 is 3. Rounded down is still 3. Times 4 is 12. So the size of the SR1, or maybe we'll call it SR prime, group for degree 14 is simply using that calculation. So this is done. This is not really related to so much to number theory, it's more of a combinatorics problem, but this helps us figure out the SR1 sign constant structures. Now let's go to the real interesting part, which is really not in the book. So now we want to look at other sine regular structures. Let me take you to the sine regular structure that we saw first, which was 2, 1. Or actually, let's use a different one. Let's say 3, 1, 3, 1, and that's subscript 8. So this is a sine regular structure, because 3 plus 1 is 4, and 4 is half of 8. What if we divide this 3, or we split it into 3 sectors? So we end up with 3, 1, and then 1, 2 plus 3, that's 5. So that gives us 3, 1 to the power of 5 subscript 8. This looks different. This is a much more extended structure. It has 6 parts, so it has a lambda of 6, but it is sine regular because the 3's and the 1's, they all have arcs of equal length when we look at degree 8. So this adds an important complication layer which I did not address in the book. So we will say when lambda is greater than 4, so the order is greater than 4, we will call these SR2 sectoral structures. So we saw this example. Another example is 5, 1 to the 7 subscript 12. There's also some more interesting examples where we don't have to split them into single sectors. So 4, 2 to the 4th subscript 12. So notice here 4 plus 2 is half of 12, so that works. So ideally this would be 4, 2, 4, 2 subscript 6. We can open up one of these 4s and turn it into 2 2s. And then we have this sectoral structure. So now this makes it really more challenging to figure out where to begin with this set. So what we will begin with is the following. We say that we will still begin with the same equation, wj plus wi equals n over 2. We figure out wj, and then after that we try to extend it into the wi. Let's look at an example. So let's say we want to look at the degree 10 structures. Half of 10 is 5, so we want wi plus wj equals 5. So this can be 4 plus 1 or 3 plus 2. 4 plus 1 gives us 4, 1, 4, 1. And then we can open this up and it will turn into 4, 1 to the 6, subscript 10. Now we can also rearrange this in several ways. So this can also be 1 comma 4 comma 1 to the 5th, subscript 10. We can also write it as 1 squared 4 1 to the 4th, or it can be 1 cubed 4 1 cubed. So for this single change that we made, we can express it as 1, 2, 3, 4 different possibilities. And in this case, the 4 is a coincidence. Now then we have 3, 2, 3, 2. We can write this as 3, 2, 3, 2, subscript 10. But we cannot open this up in any meaningful way, because we want to open it up in a way that preserves the sign. So what does that mean? That means either I have to open up the 3 into parts of 2, which doesn't work, or the other way, which also doesn't work. So therefore this only works if B divides A. And now we start seeing why number theory will creep into this equation. So this can only work, the SR2 structures, if the second part divides the first part. Of course, if it's 1, then that always divides whatever other part there is. For example, let's say we have this 6, 3, 6, 3, subscript 18. This is an SR1 structure. It is sign regular or sign constant. I can open up this 6 into 2 3s. So this can become 6 comma 3 cubed subscript 18, and this is still sign constant because this was a factor or a divisor of this. And then I can rearrange this as 3, 6, 3 squared. And that's it, really. So there's really 2 ways to express this. So you can see there's many layers of complication, and it's going to be really surprising how beautifully it simplifies. So where do we even begin by simplifying these? Let's begin by writing a general formula for what an SR2 structure really is. So AN is a type 2 or a kind 2 sectoral sign constant structure if it can be expressed as follows. AN is equal to k to the power of -1. Sorry, k minus 1, not to the power of -1. So AN equals to k minus 1, comma, 1 to the power of k plus 1. So really beautiful, really simple. So if I can express a sectoral structure in this format and then subscript 2k. So I can even change this to A subscript 2k. So if you see something of this format, then that is immediately a type 2 sine regular structure without having to worry. So let's say we have A18, and then we have half of 18 is 9, 9 minus 1 is 8. So 8 comma 1 to the power of 9 plus 1, which is 10, subscript 18, then that is a sine regular structure of the second kind. But also we said that whenever we have a structure like this, we can rearrange it by moving some of the ones to the left or to the beginning. So this can be 1, k minus 1, 1 to the k, or 1 squared, k minus 1, 1 to the k minus 1, and so on. So the question is, how many sectoral structures of this form can we create from a single structure? So if we started out with 8 comma 1 to the 10th, how many ways are there to rearrange this and keep it as sine regular? So here we will define something, and it's a pretty simple calculation actually. So we will say that if we have a structure of this form where we have a 1 to the power, then we will call these irreducible SR2 structures, because they are indeed irreducible. If you remember, irreducible means if you apply the Dal function, you get the same sectoral structure. So there's nothing isomorphic to it that is smaller in size or in degree. So we will put an I before it. So irreducible SR of subscript 2k. So here I is irreducible, SR is sine regular, 2 is the second kind, and 2k is the degree. It's a very easy way to calculate the total number of sectoral structures that meet this criteria, and it will simply be the floor function of k plus 3 divided by 2. So very straightforward. Another way you can express this will be as we round up. So the ceiling function of k over 2, and then you say plus 1 outside of the brackets, but I find this easier. So floor function of k plus 3 divided by 2. So what are we really counting here? If we have 8 comma 1 to the 10th, we're counting how many ways can we rearrange this. So we start with 1 to the 10th at the end, then we move 1 to the left, so we have 1 to the 9th, we move another 1 to the left, we have 1 to the 8th, we move another 1 to the left, we have 1 to the 7th, and then we move another 1 to the 6th, and then 1 to the 5, and then we can't go any lower. So in this case, we got 6. Because remember, sectoral structures are equivalent under reverse symmetry. So once you reach less than 5 and you start going lower, you can simply reverse the old sectoral structures. So in other words, one more time, the number of irreducible sine regular structures of type 2 that are degree 2k is equal to the floor function of k plus 3 over 2. And remember, we are only talking about even degrees. This does not apply to odd degrees. And the other caveat here is that this only begins to work when we start counting k greater than 2. So we have to start at a k of 3 or greater. And for whenever k is 1 or 2, we will immediately assume it is 0, because these structures immediately get reduced to type 0 structures. So the summary here, if k is 1, then the size of the irreducible SR2 is 0. If k is 2, it is also 0. But then once it is 3 to infinity, we simply use this floor function. But this does not give us all of the type 2 signed regular structures within a given set. This only gives us the irreducible ones. So what do we do? How do we figure out the rest of them? So we will say that the entirety of the SR2 set of degree 2k is the union or the sum of the two sets, because they are disjoint. It will be the union of the irreducible SR2 structures and the reducible SR2 structures. So we looked at the irreducible ones. Now we can put those aside. Now let's look at the reducible ones. So the reducible sectoral structure means that if we do the dal of that function of that sectoral structure, we get another one that is smaller. So what is the general form for these, or what do we know about these structures? We saw an example earlier. We saw this, for example, for 2, which became 4, 2 cubed, subscript 12. So they have the general form A times B, in this case 2 times 2. Maybe we'll use a different example. And the second part is a to the power of x. So here, for example, we had, let's try something different. Let's say 6, 3, 6, 3 can be expressed as 6, 3, 1, 2 to the 4th, and that is all subscript 18. So this can be written as 3 times 2. So that's A times B. And then this 3 is written as A to the 4th or A to the x. So A times B, A to the x, such that the sum of these adds up to 2k. So AB plus, we have xa's, so ax must add up to 2k. So that's the general rule for the reducible type 2 structures. However, because they are reducible, then they must be isomorphic to something else. And that something else will end up being an irreducible SR2 structure of a smaller degree. So we will say A2k or A subscript 2k is isomorphic to another sectoral structure that can be expressed as j minus 1 comma 1 to the j plus 1, which is the exact same thing we saw here, but we change the k to a j, subscript 2j, such that k is equal to a times j. So this is the conversion factor. So we can write this instead of an isomorphism as an equality. So we will say A2 subscript 2k is equal to A times j minus 1 comma A to the power of j plus 1. So we're multiplying everything by A basically. We're multiplying everything here by A. Subscript 2aj. So here we took this and we multiplied everything by A. All right. So therefore, the size of all the SR2 structures or the signed regular structures of type 2 that have a degree of 2k is equal to, the size of this whole set is equal to the sum of all the SR2 structures contained within. So this will include all the irreducible structures, which we know how to calculate as K plus 3 over 2 floor, plus all the sectoral structures that contain parts that are divisors of K. So for example, we will say the first part, so here we had 6363, that is reducible, that's not irreducible. So here we will say K, so K in this case that's 2 times 9, so K is 9, divided by one of the divisors of 9 is 3, so 9 divided by 3 is 3, plus 3 is 6, divided by 2, we're back to 3. So what does this mean? So we start with the number of irreducible sectoral structures that are SR2, and then we want to find all the reducible sectoral structures that are isomorphic to irreducible ones. So the total number, for example, here will be the first divisor of K, so K divided by its first divisor, plus 3 over 2, and we take the floor function, and we do this for all the divisors of K. In doing this, what we're really doing is we are saying it's hard to calculate the reducible sectoral structures directly, so we're finding a group isomorphism in the group's theory setting between the set of reducible structures of degree 2k and or part of this set and the irreducible sectoral structures that are SR2 of another set. And we keep adding this until we account for all the divisors of K. So let me show you an application of this so it makes more sense. So let's say we want the SR2 structures of degree 20. So 20 is 2 times 10. So in this case, K is 10. So we will say this is equal to K, which is 10, plus 3 divided by 2 floor function of that, plus we go to the next divisor, so that let's go through the divisors of 10. So we have 2. However, we said that when K is 2, then this function is equal to 0. So we will say 0 whenever there is a 2. 1 is also a divisor. So for 1, we will also say 0, because whenever it's 2 or 1, we say 0. Next, we have 4. 20 divided by 4 is 5. So we will say, we want 10 divided by, we want the divisors of 10, not 20. So we're focused about K. So 5 is a divisor of 10. So we will say 5 plus 3 over 2 floor function. So we have 4 divisors for 10. We've got 1, 2, 5, and 10. We always exclude the 1 and the 2 because they're going to give us a result of 0. So we are left with 5 and 10. So we will say, we will apply this formula to 5 and 10. And that means 10 plus 3 is 13, divided by 2 is 6.5, floor function is 6. 5 plus 3 is 8, divided by 2 is 4, equals 10. So there are 10 sectoral structures of degree 20 that are sine regular type 2. And I know this can be a little non-intuitive, but I promise if you just pause and think about it a little bit, it makes perfect sense why this is isomorphic to another set. There's a direct relationship between the reducible and irreducible sets. So what's the general formula that we can see? So the size of an SR2 set of degree 2k is equal to, and again here we will use this notation from number theory, the sum of the divisor functions such that for each divisor we will say the divisor of k, so all the divisors of k, plus 3 divided by 2 floor function, starting with a divisor that is more than 2. So here I might have created a little bit of confusion. So it's easier to think of the divisor itself when we're using these equations than to actually divide the original number by the divisor and generate them in reverse. So what do we want? We want first, let's say we have degree 100. So we say 2k is equal to 100, therefore k is equal to 50. Next, we list all the divisors of 50. We exclude 1 and 2. So starting from 5 in this case. And we count all the other divisors. For each of these divisors, we apply the equation divisor plus 3 divided by 2 floor function. So this is much simpler. So divisor, so let's say 5 plus 3 is 8 divided by 2 is 4. So we say 4. And then we do that for each of the divisors and we add them. And this is a very common way of expressing functions in number theory. So this is a type of divisor function. So basically divisor functions will be divisor of x, f of x. And in this case, f of x is x plus 3 over 2 floor function. But the key is you have to exclude 1 and 2 because those are equal to 0. So what happens when we generate this sequence for the SR2 structures? We get a very specific numeric sequence for the sizes of the sets. And here we're going to list them in, because this only applies to even numbers. So for sets of degree 2, 4, 6, 8, and so on, we get the sizes 0, 0, 3, 3, 4, 7, 5, 8, 9, 10, 7, 17, and so on. So a very unique sequence. Now what I also want you to notice is that for very large values of k, which is really where this becomes most useful. So let's say we're looking at degree 10,000 or degree 50,000. So for very large values of k, the size of the SR2 set of degree 2k is approximately equal to, and here if you see, we can turn this into two summations as follows. We can say that this is equal to the summation for the divisors of k. We turn this into a ceiling function and we take the 1 out. So this becomes divisor divided by 2, ceiling, and then plus 1. I find this less intuitive, but this will be easier for this calculation. So the sigma for this plus this, we can turn it into sigma of the first expression plus sigma of the second expression. So this, the first part, is approximately equal to the S function, or the, let's call the sigma 1 function. The sigma 1 function in number theory is, instead of counting the divisors, we add all the divisors. So here we get approximately half of sigma 1 of k. And the larger the number, the more this approaches half of sigma 1 of k. For large enough numbers, it's practically identical. So half of sigma 1 of k plus, we're left with this 1 here at the end. So sigma 1 for the divisors, and this is simply the divisor function sigma 0, which counts the divisors. So plus sigma 0 of k. So for very large numbers, this is approximately equal to half sigma 1 of k plus sigma 0 of k. So this is really amazing that we have such a deep number theory relationship from just a geometric concept, actually even a trigonometric concept. Now for very large numbers also, that this will become much larger than the second part, so making this a little bit less relevant. So really for very large numbers, this is approximately half of sigma 1 of k, but this is more thorough to include both. So this was really the main finding of our study today. But now let's bring it all back together. So this, for a sectoral set of degree n or a degree 2k, because it has to be even, the total number of sine regular structures is the sum of the sine of the SR0 structures, the SR1 structures, and the SR2 structures. And again, the book was missing the SR2 structures. So therefore, we can substitute for each of these what it equals. The first one is Q0, just the regular divisor function. So not Q, sorry, sigma 0 of 2k. The second one we said is equal to 4 floor function of k minus 1 over 2. And the third one is sigma of all the divisors of k that are greater than 2, such that we say divisor plus 3 divided by 2 floor function. So we have now all these three into a single equation. And we generate a very unique number sequence for the total number of sine regular sectoral structures. And if we didn't go through all this geometry and through all this number theory, this sequence will be almost impenetrable. There's no way to figure out where this sequence is coming from. It took me a long time. So the sequence is 2, 3, 11, 11, 16, 21, 21, 25, 31, 32, 31, 44, and so on. I hope I didn't make any calculation mistakes. But actually, for all of these, I counted them geometrically first. We noticed that approximately the size of SR2k is approximately equal to sigma 0 of 2k plus sigma 0 of k plus half of sigma 1 of k. Again, this is for very large numbers. Let's say for large values of k plus 2k. Because for large enough numbers, this will reduce to just simply 2k. So very nice way of relating the the sigma 0, the sigma 1 functions, and this concept. Now let me show you one final interesting thing. What happens if k is a prime number? So let's say k is 11. In this case, 2k is 22. So if the degree of the function or of the sectoral structure is 2 times a prime number, 2p, then the size of SR 2p is equal to, first, the divisor, the number of divisors of 2p, and that will be 1. It will also be 2. It will be p and 2p. So that's 4, always going to be 4. And then we go to this next part. We replace k with p. We say p minus 1 over 2. And again, since we're only looking at odd primes, p minus 1 will be an even number. Divided by 2 will not give us any fraction. So we can really get rid of the floor function. So this gives us 2 times p minus 1. And then for the last part, the summation, we're excluding the divisor 1, we're excluding the divisor 2. We're left with 2 divisors. Those are p and 2p. So therefore, we will say that this function will can be replaced by p plus 3 over 2, because if you keep in mind, we're actually looking, when we're doing this summation, we are only looking at the divisors of k, not of 2k. I keep making this mistake. And many times when I made errors, it was always that point. So here we're really looking at the divisors of p, not of 2p, when we're doing that third part of the equation. So for each part, really look at what we are using. So first part, we are using 2k. Second part, we're using k. Third part, we're using k. So for p, we really have only 1 and p. We can't use the 1, we can use the p. And this will be this equation here, p plus 3 divided by 2 floor function. Since p is odd plus another odd number, we get an even, so there will be no fractions. So the floor function is obsolete. So this becomes p plus 3 over 2. We simplify this and we get this very simple equation that the size of SR2p is equal to 5 over 2 times p plus 1 and then plus 1 to that. I don't know why I find it easier to write it this way. So 5 over 2 times p plus 1 and then plus 1 to that. So a very simple linear equation, which was very surprising to me when I found it. So this applies to the structures that are of the form 2p. So here we have 11, 16, 21, 31. All of these are the result of this direct linear relationship.